Wow. Hi, my name is Pablo Halpern. I am the guy who coordinates parallel language development at Intel. And I'm here to talk about parallelism in C++. This is an overview talk, so we're just going to kind of touch on things. You're not going to come out here, with being an expert in how to do parallel programming in C++. But what I do want you to get out of this talk is a sense that this is for real. People are programming using parallel programming techniques. They are doing it in C++, maybe even more than other languages, because C++ is a performance language. We've got the questions that I want to answer, but the most important thing that I want you to get out of this talk is this is happening, and you kind of need to be in on it. Okay, so the what and why. What is parallel programming? Okay, so I have this kind of like silly little discussion diagram here. We know what parallelism is in geometry, right? The parallel lines, they're on a plane, they don't intersect each other. Parallelism in computation comes from that same idea. You have independent tasks, they don't interact with each other, or they have minimal interaction. As we'll learn, it's kind of impossible to completely eliminate interactions among parallel tasks, but you minimize them. And one thing I do want to point out is this, wrong button. Where am I? This last circle here, so we have here, each of these circles represent a task or a part of a task, and you've got the purple tasks and the yellow tasks and the green tasks. In parallel, they have minimum interactions, but when they come back together, they join here at this red dot. That is a point of interaction, and it's actually a little bit of a point of friction, as we'll see, where you can get in trouble with parallel programming. So why do we have to go parallel? Well, you want your program to be faster, right? You want to use less battery, less power. But why is it that, computers have been getting faster and faster. Why is it that we have to go parallel?
CPU's speed is limited, no more.
That's exactly right, and that's what. So, I'm sure you didn't hear what he said. Everybody in the room. I was kind of expecting like 6 people or something like that. We would sort of sit around in a circle, So, I'm a little overwhelmed. So I'll repeat the statement here. Yes, speed is limited. The speed isn't going up anymore, as the diagram here shows. We have the transistor count still going up. It's Moore's law. But the speed is topping out, and 5 gigahertz is kind of an upper limit. Most of the CPUs you really want to keep below that. And the reason for that is that we hit this kind of heat wall. As the trend was going on in the 90s and the 2000s, the transistor count was going up, the clock rate was going up, and the heat density was going up, the amount of heat generated by the CPU chips. If it had continued in that line, you would have seen the trend go up like this. Now remember, this is a log scale. So each of these markings is 10x, right? So we're at the temperature of like a hot plate. If we kept going, we would have gotten to like a nuclear reactor. Kept going, rocket nozzle, and then maybe the sun's surface. Captain, can't take much more of this, Captain. So we had to do something, and what the vendors did is they went multicore. They said, well, we keep having all these extra transistors, so instead of making one core more complicated, they already kind of run most of the internal parallelism out of these cores. They started putting multiple cores on a chip. You could run 2 cores at half the speed and get the same compute power as 1 core, but you use a lot less energy, like an eighth, because there's the formula for energy consumption based on frequency is linear, but voltage is also based on frequency, and that's quadratic. So total, you have almost a cubic increase as you increase the clock rate. All right, so 4 cores is even better than 2. 8 cores, 16 cores. We're at a point now where let me get the numbers here because I want to be accurate with this. A Xeon E7 has up to 15 cores, and each core is hyper-threaded, so it's as if it were 30 cores in a sense. A Xeon Phi has 57 to 61 cores, and it's 4x hyper-threaded. And in addition to the cores, they've added vector lanes, which we'll get to a little bit later, where you can do more than one. With one instruction, you can operate on more than one piece of data at once. All right. So multicore is here to stay. Parallelism is necessary to program multicore. And so that's why it's happening. That's why we have an entire track at this conference about parallel. And this is like the first talk in that track. Who thinks that concurrency and parallelism are the same thing? Well, it's kind of a leading question, right? I wouldn't be asking this question if I thought the answer was yes, right? There is a relationship between them, but they are definitely not the same thing. Concurrency is about these interacting components. You've got, for example, a UI thread, and it's talking to a compute thread, or maybe an I/O thread, and they're exchanging messages between them. You can write a concurrent program on one core. You do not need multi-core hardware to have a concurrent program. In fact, they've existed for quite a while. The idea of a separate UI thread came about when most PCs had one core. Parallelism doesn't care about one core. If you have only one core, if you don't have parallel resources, you gain nothing from parallelism. It's about exploiting the hardware. That's its purpose. And to do that, you want minimum interaction among the threads, the opposite of interacting components. You want non-interacting components. Here's a sports analogy. Basketball is a concurrent sport. You don't play basketball with one player. You have to have at least 2 players, and preferably 10 players on the court at once. They are interacting. The opponents are interfering with each other. The teammates are passing to each other. They have roles. They have to be doing things concurrently. On the other hand, running, or track and field, is more a parallel sport. So all of the runners are independent. They should have as little interaction as possible. They'd better not be tripping each other up, right? And maybe they'll look over their shoulder, but that's about it as far as interaction between the runners. The only thing that limits how many runners you have is how wide is your track. How many lanes do you have on your track? If you have a 1-lane track, you can still do a track meet. You just have to use a stopwatch to time each runner, right? So that's parallelism. So other examples, golf, parallel, right? It's pretty much an independent sport that you can have more than one golfer on the golf course at once, but they could be in different parts of the golf course, and they could be playing on different days, and you can still get a final score at the end. Football, baseball, those are concurrent sports. They interact. In the workplace, if you look at something like TV production or movie production, that's concurrent. Interaction, the director and the actors and the camera people all have their roles, and they have to be doing them at the same time. Something like sorting mail, parallel. You can have 2 people sorting mail approximately twice as fast as 1 person sorting mail, right? Just add more people. At a certain point, they'll begin to interfere with each other as they try and stuff the same envelopes into the same box. But up to a limit, you can just gain speed by adding people. And that's really the goal of parallelism, right? You want to be able to scale your program up. So more CPUs, faster program. More vector lanes, faster program. That's the ideal. Let's talk a little bit about the concepts and vocabulary. I seem to have 2 microphones. When I get close to here, so forgive me that. The parallelism, we talk about parallelism, people think about program structure. People think about the actual notations you put in a program that says this is parallel. But the parallelism exists in the program even before you add those notations. It's a property of the algorithm. So here we have an algorithm expressed as a bunch of tasks, a bunch of subparts. They have dependencies between them. The arrows are the dependencies in reverse. The arrows are the control flow, and the dependencies are the opposite of the arrows. So each of these bubbles represents some sort of task or subtask, and they, as you can see, the you have to complete task A before you get to task B or to task F. So in the graph notation, which is this mathematical notation, A precedes B, A precedes F, all right? And that is shown by this funny less than symbol. It looks like a less than symbol, but it's kind of curvy. That means precedes, all right? There's also succeeds, and then the important one is in parallel with, all right? So B and F are in parallel with each other. And K and H are in parallel with each other. And K is in parallel with A, B, and C. I'm sorry, B, C, and D. So this exists whether the program has been explicitly made parallel or not. And there's certain languages, like some functional languages, that will take advantage of this. They can actually see the entire graph, and they can run things in parallel even without you putting any kind of parallel notation in. C++ is not one of those languages. There's several different kinds of parallelism. We're going to be talking mostly about fork-join parallelism today, but it's important to note that there are other kinds. Fork-join parallelism is what the graph on the previous page shown. You start with a single task. You fork out into 2 or more tasks. They run in parallel. You join back together into a single task. It is compositional, so any one of the tasks running in parallel may have forks. As we saw in the previous slide, G is also a parallel task. G forks out. You end up with tasks that are in parallel with each other and also in parallel with anything that G is in parallel with. Okay, so it is recursively parallel that way. Sorry. Vector or SIMD parallelism, which are not exactly the same thing, but I'm going to talk about them as if they were the same. SIMD is a kind of a subset, is actually a subset of total space of vector programming. That is when a single instruction operates on more than one piece of data at once. So we show here the first column is a single instruction operating on 4 pieces of data. When it's done, the next instruction runs on 4 pieces of data and so on. If there's a control flow divergence, so there's an if statement somewhere in there, and some of the lanes follow the if and some of them don't, well, there's a way to handle that, but you lose some of the parallelism when that happens. So in vector programming, you want to minimize control flow divergence. You tend to use it mostly when there's minimal control flow divergence. The last one that I show on the slides is pipeline parallelism. It's an interesting kind of parallelism, and it's fairly common in algorithms. There's different ways to attack it. We show that A is a task, and its output feeds into B, and then the output of B feeds into C. So those are clearly a dependency chain there. You can't run B until A is complete. You can't run C until B is complete. But if you have a stream of data coming in, as soon as A is done, you can start A again, the A stage again, on the next piece of data. So it is running now in parallel with B, and you go on again, and you build this pipeline like that. There's another kind of parallelism not shown here, which is graph parallelism. It's not shown here because I can't figure out a way to draw it. But it is kind of an extension, a generalization of pipeline parallelism, or you can think of pipeline as a specialized case of graph parallelism. And this is where all of the stages of your computation are chained together in such a way that as soon as the dependencies for one stage are met by the previous stages, it can fire off and execute in parallel. It's the most general form of parallelism. It's also very hard to write in a programming language. It's been done, but it's complicated. So I'm going to take an example here. We're using fork-join parallelism as the model in most of the talk here. This is the world's worst way of computing a Fibonacci number. And yet it is the favorite of people in parallelism to compute Fibonacci numbers this way. Why? Because it's all simple compute. It breaks, so it's a recursive algorithm for computing Fibonacci, and we have the two you know, the nth Fibonacci number is the sum of the nth minus 1 and the nth minus 2 Fibonacci numbers. So if we pass in n, we simply compute recursively the nth minus 1 and the nth minus 2 Fibonacci number, and then we return the result. Okay, is there any parallelism here? Well, yeah. As you can see, I've numbered the statements, A, B, C, and D, and clearly you cannot compute B and C until A is complete, because you may not want to, because the if statement might say don't do that, right? So clearly there's a dependency between A and B and between A and C. But there's no dependency between B and C. They are completely independent computations, and therefore could be done in parallel, theoretically. So let's do them in parallel. The notation I'm using here is from Silk Plus. Silk Plus is an extension to C and C++. It's available in GCC. There's a branch of Clang that has it, and it's in the Intel compiler. So it's available. And I use it because it's actually the simplest notation for fork-join parallelism that I've seen anywhere. The spawn statement simply says, do this, but you don't have to wait for it to be done. In other words, an asynchronous call. In the case of the Silk runtime, that means that it's actually going to go and execute fib n minus 2, but some other core could come in and execute the continuation, which is the fib of, I'm sorry, it's going to execute fib of n minus 1, and the continuation fib of n minus 2 will happen if there are resources to do it. If there are not resources to do it, that is, there's no idle core out there waiting for work to do, it's going to execute fib of n minus 1 and then come back and execute fib of n minus 2. So it is completely scalable depending on how many cores you actually have and how many are actually idle at any given time. Yes, question?
How is it different from STD async, for example?
I will get to STD async. So the question is, how is this different from STD async? The form looks very similar, but the mechanics are very different, and I'll get to that later. Thanks for the question. The Silk sync is a statement that says, don't go past this point until everything asynchronous above it is complete. Okay. There's an implicit sync at the end that's not really important in this example, in case there's anything still running. The implicit sync is important because it gives you composition. It lets you know that if you call a function, it acts like a normal function. It returns when everything's done. Okay, so this is the Fibonacci example shown as a parallel program. But how much parallelism is actually here? It looks like we're just doing two things at once, but we're not. We're doing more than two things at once because it's recursive. At the top level, we're doing two things at once. And then in the next level, we're doing two things for each of the two things, right? So the entire left half of this tree is in parallel with the entire right half of the tree. And then the leftmost quarter is in parallel with all the other quarters of the tree and so on. This is a very small example here where we're computing the 4th Fibonacci number, but if we were computing the 100th Fibonacci number, it would get very bushy, right? And so that's a lot of parallelism possible here. So as we spawn down the tree, we're getting to smaller and smaller, Fibonacci, so we get down to fib of 0 at the very bottom. As we sync back up, we're collecting the partial results and adding them up until we return them to the very top. Good? This is a more realistic example. It has pretty much the same structure as the fib. It shows, this is quicksort. In quicksort, we partition the array into two halves, and then we sort each of the two halves. The partition is a serial step, and the sort, once you've partitioned it, though, the two sorts, the recursive sorts, can happen concurrently. So we have the same recursion pattern as we did for fib. This one does use the implicit sync at the end of the function. I used that specifically because the slide was getting too crowded and I didn't have room for one more line. Okay, so that's the basics of what makes up fork-join parallelism. What is available in C++ to do it? Well, we've already seen Silk. I'll introduce it again. But we have, I'm going to introduce you quickly to 4 different frameworks, languages, whatever you want to call them, for doing parallelism in C++. The first I'm going to show you is a library approach taken by Threading Building Blocks, TBB, and that's from Intel, and PPL from Microsoft. They are very similar libraries. TBB is a bit older and has a few extra features, as we show here. So starting with fork join parallelism, the way you do that in TBB is you create this thing called a task group. And the task group lets you add tasks. And then at the end, you can wait for the tasks. So adding tasks, that's the equivalent of the silk spawn we saw. And then the wait is the equivalent of the silk sync. There's a couple of other constructs in TBB that get the same basic effect. But this is the most general. There's also a parallel loop. So a lot of people, especially people who learned OpenMP 10 years ago, think that parallelism is about loops. And there certainly is a very important subclass of problems that can be solved by taking a loop and executing all the iterations in parallel. And because it's such a common subclass of problem, every parallelism framework I've seen has some way of doing a parallel loop. And this is the way TBB does it. So this one, you see, really takes advantage of the fact that C++11 introduced lambdas. It was much more cumbersome to do before. It's a function call. This is actually a template function called parallel for. You take the arguments, 0 to n is the range of the loop. It goes from 0 to n minus 1. And then it calls this lambda with each value of the argument, or each value of the loop counter. Okay? And it calls them in parallel. So it doesn't wait for iteration 0 to complete before starting iteration 1. TBB also has support for pipeline parallelism. There's a construct that this is one of 2 different ways that you can create pipelines in TBB. But the idea is that each stage has to be packaged into this thing called a filter. And that's what the make filter is done. So this is a 3-stage pipeline. It gets a token, it does some kind of lookup, and then it does some kind of processing on that token. Okay, don't have time. Again, this is an overview. I don't have time to go into detail how this works. But you get the idea of building this thing up and building up this object of these stages. And then it runs. The first stage has to run serially, which means that you can't start the second iteration of the first stage until the first iteration is complete. But the second stage can be done in parallel. So it's saying second stage can run in parallel with each other, with the other second stages going on simultaneously. And recently, TBB added graph parallelism. This is really complicated to express, and that's why I did not even make an attempt on the slide to fit it in. But suffice to say, it's similar to pipeline that you create a graph object. There's a bunch of different ways to add nodes, graph nodes to it, and link them together into a processing chain such that when one graph node is complete, its input can feed into the next graph node, and when the next graph node, all of its inputs are ready, it can run in parallel. OpenMP, possibly the oldest still present attempt at adding parallelism to C++. It also works in C and in Fortran. So if you want to write a Fortran program that mixes C, C++, and Fortran and uses parallelism, OpenMP is the one for you. OpenMP is a pragma notation. Its intention was that it's kind of laid on top of C++, and that the pragmas are ignored if your compiler doesn't support parallelism. It kind of works that way. There are ways in which the semantics change a little bit when you add these pragmas, and so you have to be really careful if that's what you really want, is to be able to compile the same program serially and in parallel. You have to be really careful. But the idea is it's a pragma notation. And back to our QSort example, we're sorting the first half of our partition set, our second half, and we're doing them in parallel by designating each of them as a task. And then we're waiting for all the tasks to complete. OpenMP also has a parallel for, and it looks like a for loop. Wow, imagine that. So there are constraints like the loop counter has to be a random access thing. It has to behave like an integer, so or a pointer. Right? It has to be something that you can add to and subtract from, get the difference between them. You have to know exactly how many iterations the loop is going to execute before the very first iteration even runs. Right? And that's common for all of the parallel for loops that the different languages have. There's very recently in OpenMP 4, they added vector parallelism. It looks just like that parallel for loop. The one thing that's interesting here is that they added this thing called a SIMD-enabled function. I don't have the syntax for declaring that on the slide, but there is a pragma for saying this function is, we expect it to be called in the vector context. All right, and if a function is compiled with that pragma, then when you call it in a vector context, it extends the vector context of the loop into that function is the best way to think of it. So the function will operate, so if you have like 4 wide vectors, the function will be compiled both in a normal scalar form, but also in a 4 wide vector form. And so if you have a 4 wide vector loop, it'll pass 4 values to the function at once and give you all of the performance that you would get as if you inline that function right into the loop. And you've seen some of Silk Plus already. You've seen the spawn and sync. There's also a parallel for in Silk, the Silk 4. And this is also available in C as well as in C++. The vector-enabled loop looks just like OpenMP's. That's not an accident. It was first in Silk Plus, and then people that were working on Silk Plus went to the OpenMP committee and said, look, vector. And OpenMP committee liked that. It's kind of an accident that it was a pragma at all in Silk Plus, and in the Intel compiler, we've already started moving towards a keyword syntax to do the same thing. In addition to the vector loop, Silk Plus has this array notation that lets you kind of hide the vectorization in array operations. So what we have here is a function G being called on an entire array. Now, it's not passing the array into G. What it's doing is calling G repeatedly in a vector context. So if G is SIMD enabled, it will give you all that vector speed up. So there's kind of an implicit loop around that whole thing. Anybody who remembers APL will know a little bit of the inspiration for array notation. There's no pipelining in Silk Plus at the moment, but it is in the lab, and you can get the experimental stuff off the website. And in addition to these constructs here, Silk Plus supports a thing called hyperobjects, especially for reduction, which we'll get to a little bit later, that is kind of unique. And we haven't seen it in any other language. Time check. Let's see, I'm doing pretty good. Okay. If we want to speculate about what kind of parallelism will end up in the standard someday, this is the kind of stuff we've been working on. The task region construct is it's a scoped area of parallelism. The idea being to get proper composition, you want to say, and OpenMP has this as well. I didn't show it on the slide. You want to say, I'm going to go parallel in this range. Now, it doesn't mean that you can't go parallel outside the range. It means that you are composing. You're saying, I have a nested parallel region within possibly another parallel region. And at the end of this, any parallelism that started inside this region will have stopped. It will be back to a single strand of control. So a task region is it's a template function, and we're passing here a lambda in there. And within the lambda, we can call run on the handle that was generated by the task region. Okay, and there's our run right there. So this is back to our QSort example. This is how you would do it with the task region and task run in the proposed standard. So this is actually moving through the standards process right now. It's expected to be in a technical specification not too far in the future. Technical specification, for those of you who are not deeply involved in standardization, the technical specification is kind of like an experimental standard or a pseudo standard. It's not a standard. It doesn't carry the weight of a standard. It can be changed at a moment's notice by the committee that put it out. But it is encouragement. It is, you know, a spec written to the quality of a standard, meaning all the I's are dotted and the T's are crossed as best we could do, that encourages implementers to go and implement it and people to experiment with it and then feed that information back into the standards process so that eventually it moves into the standard in some better form than the technical original technical specification. So this is moving towards a technical specification. The for each loop also moving towards a technical specification, similar to the one we saw in TBB. There's a version of the for each where you specify that in addition to parallelization, you want vectorization. And there will eventually, as we hone the language a little bit better, have something for vectorization only. So there's parallel, there's vector, and there's both. Right now, there's parallel on both, but there's not plain vector in the current draft of the technical specification. The other thing that's further back in the process is a language form of doing vector loops. We'll see where that goes. C++ currently has constructs for concurrency. This is good. We want that. But don't confuse it with parallelism. So this gets back to the question about async and the difference between async and what we saw with silk spawn. The correct use of concurrent constructs is for concurrency. So the first box here, we see a work thread being created to actually do some important computation. And then while that's running, concurrent with it, we run our event loop. Presumably, the event loop feeds into the work loop in some way. There'd be some sort of message passing and so on. When all of that is done, we join together, we end the work thread, and we're done. That's a good use of concurrency. The next one is not such a good idea. Create a thread to do some piece of work in parallel, and then do the work in parallel and join. What's wrong with that? You know how expensive it is to create a thread? It used to be considered that thread creation was cheap because compared to creating a process, boy, a thread was really cheap. But compared to something like a silk spawn or a TBB run, creating a thread is a couple of orders of magnitude more expensive. And it uses up resources. So if you have a recursive algorithm like quicksort, you could blow out your resources on a machine, even these huge machines we have today, right? So not recommended. Async has exactly the same problem. It's really just another way of spelling the same thing. There is a little bit more wiggle room in async to avoid blowing out your machine, but it's not going to be efficient. It just wasn't really. There were some hopes when it was introduced that it might be useful for parallelism. It really doesn't seem to have that potential. So async is still great for certain concurrent things. But it's not the way you want to do parallelism. Now, one thing you can do is you can take the concurrency constructs and you could build a parallelism library, right? You could say, let's create a thread pool so you don't have to create threads all the time, and let's load balance among tasks and have some sort of task queue mechanism and so on. And what's wrong with that? Well, there's only one thing wrong with that, and that is that you'll be reinventing the wheel, because TBB has already done that. PPL has already done that. OpenMP, Silk, they've already done that. And it's a lot of work. All right? You can get something up and running in a day. You want it efficient, it's going to take a lot longer. Okay? So don't reinvent the wheel. I mean, you've heard that before, right? Okay, so clearly, question?
So you're saying that it's not a good idea to use parallelism constructs for
Concurrency constructs for parallelism. It's not a good idea to use concurrency constructs for parallelism, right?
Would it be a mistake to use parallel constructs for concurrency, and so what's wrong there?
Ah, okay, so the question is, if you don't want to use concurrency constructs for parallelism, is there any problem doing it the other way around, using parallelism constructs for concurrency? Yeah. I don't have an example handy, but there are cases where it'll just kind of work. But the problem is that parallel constructs are intended for maximum exploitation of the hardware. If you don't have extra hardware, extra resources to do something, something will not run simultaneously. Okay, we showed that with the fib example, that you spawn fib of n minus 1, and then if there happens to be another CPU available, it'll run fib of n minus 2 concurrently. Otherwise, they run one after the other. Okay? That means that if fib of n minus 1 and fib of n minus 2 want to exchange messages, you'll deadlock, because fib of n minus 2 is just sitting there waiting for fib of n minus 1 to finish. So if there needs to be communication, if it's truly concurrent, then the parallelism constructs will not do the good job. OpenMP has in fact been criticized because some of its constructs really have some concurrency kind of built into them. And the spec says this will run on separate threads. And this kind of muddling of the two it encourages some poor practices and things that don't translate well into other forms of parallelism. Okay, so be wary of that. OpenMP, I think, has been moving more towards really cleaning up those things. But once you've published the standards, it's very difficult to sort of go back on that. Good question. Yes.
Just to make sure I understand that, so the basic difference between the standard functions for parallelism and async, which is not necessarily designed for concurrency, is that they don't operate on thread pools, and the library-based parallelism.
So the question is the basic difference between the concurrency constructs in the standard and a proper parallelism construct just that they don't work on thread pools? No, it's more of that's certainly part of it, but it's more of almost a mathematical sort of construction. Two things that are logically in parallel do not have to run concurrently. They do not have to run on separate threads, which means they had better not communicate with each other in such a way that one will deadlock on the other. That is more fundamental than whether there's a thread pool involved. Right? So yes, the thread pool certainly makes it more efficient to implement parallelism than if you spawn a thread for each thing. But the other thing is that you just don't actually have to have more than one thread. And in fact, we'll see that when you're debugging a program, you don't want there to be more than one thread. You want to run the entire program serially until you've gotten the serial bugs out. Then you run it in parallel, and then you start working on the parallel bugs, which is a separate thing. Sorry. So it's not all sort of roses and unicorns. There's got to be something that makes parallel programming hard. Otherwise, you wouldn't need to sort of come in here and go to all these parallelism talks at the CppCon to learn about parallelism. So the poster child for the problems with parallelism is the data race. Data race is when two things operating concurrently access the same data location, and at least one of them is writing to it. That causes a data race. So here we have what looks like a really simple implementation of count. All right, count is an STL algorithm, and we've just extended it and called it parallel count to try and do the same work in parallel. So we have a couple of random access iterators coming in, and we're just going to loop through them. And we're counting how many times a particular value occurs within that range specified by that pair of iterators. OK, so we're all good up to this point, because everything that's going on up to here is truly in parallel. The value is being compared to each individual item, and it's happening in parallel. Even the count, even the increment of the result is kind of in parallel. But the problem is there's only one of them. And if things are happening simultaneously, you have a data race. So looked in the graphic form, we have the for loop splitting off. That's the fork point. And a number of the parallel tasks operating on the same data location. Data race, big problem, common problem in parallel programming. So how do we mitigate it? Well, if you've been doing concurrent programming for a while, the first thing you might reach for is a mutex. And if you've been doing it more recently, you might say, maybe not a mutex, maybe an atomic, that would be more efficient, right? So this works, but they're not fast. I'll show a little bit later part of what makes these so slow, but suffice to say, it could take 20 cycles for an atomic to do its job, whereas a normal variable write is less than a cycle. So this dramatically slows down the algorithm. It may slow it down enough that you've lost all the gains you've gotten from parallelism in the first place, okay? Depending on how many cores you have. And in fact, the unfortunate thing about this is the more cores you have, you might think, okay, so I lose a factor of 2 in the speed of the loop, but I have 20 cores, so I'm still 10x better, right? Wrong. Because the more cores you have, the more contention there is on this variable, and the more contention there is, the more it slows it down. So you really might not get any benefit from this. It might actually be slower than the serial version. Okay, so not the best solution. Let's try a different one. This is reduction. Reduction is a really common, it's not inherently a parallel thing, but most people, including myself, think of it in terms of parallelism. It's taking these results from different parts of the computation and adding them together in such a way, or combining them in such a way that is both safe and efficient. Now what's going on under the covers is that the runtime system is creating separate copies of the variable, and the concurrent accesses to that variable are actually not accessing the same variable. They're accessing these separate copies, and the runtime knows how to combine them at the end. In order for a reduction to work, you need an operation that can be chained together and then broken up into arbitrary segments, like addition, conveniently enough. And addition is probably the most common reduction we see. We see here reduction shown in 3 different syntaxes. In Silk Plus, you use this hyper object called a reducer, which is a special variable that has this quality that when you access it, it has this pointer-like syntax. When you access it through this pointer-like syntax, you get a view that is guaranteed not to be racing with any other view of that reducer. And you add into that view, but by the time everything is collapsed and you're back down to the serial, all those views have been added together. Now addition, like I said, is very convenient because you can say A plus B plus C plus D plus E plus F is the same as A plus B plus B and so on. You can group it any way you want, and you'll still get the same result at the end. OpenMP, rather than having a separate kind of variable, has a way of marking a variable that says within this loop, and that's the thing about OpenMP, it's specific to a loop. Within this loop, make sure that accesses to this variable don't collide, and we'll add them together. Just as in the Silk Plus case, you have to specify what is the type of operation you use to reduce it. Unlike the Silk Plus case, if you misuse the variable, like doing a multiplication on it or something like that, or assignment to it, OpenMP won't tell you. You'll get the wrong result, but OpenMP won't tell you. Because really in a reduction, the only thing you really should be doing to the variable is the reduction operation itself. So summing in this case works because plus plus is just a form of addition. TBB has a parallel reduce. I didn't go into all the syntax there. It's not that complicated, but it would be a distraction to get into it. Again, it's just like a parallel for. That is a parallel for each, but has this extra machinery and extra arguments, so you know that it needs to do a reduction, and it actually returns the reduced value. TBB and Silk have very generalized reductions where the operation that you're doing reduction has to be associative, but it does not need to be commutative. Okay, so A plus B does not have to be equal to B plus A. So for example, it works for string append or list append or things like that. OpenMP requires commutativity. It gets certain performance benefits by requiring that, but it's a limitation as well. Question back here?
Are concepts like being leveraged for expressing the requirements, like associating, giving the requirements for the operations?
Yes, so the requirements are, yes, so I guess you could say that there are concepts, right?
No, I mean, it is conceptually a requirement, but are the concepts like as a C++ 14, are they used to express the requirements?
Yes, I haven't tried that yet, but I believe that at least the syntactic requirements can certainly be represented using concepts. Yes. So the question was, can the concepts that is being proposed for C++ 17 or a technical specification, I'm not sure what path it's on right now, can they be used to describe the requirements for these operations? And I think on a syntactic level, yes. There's certain semantic things that you cannot express that way. Okay. Data races I'm spending a lot of time on because they're one of the most important parallelism errors you'll run into. One of the things about data races is it's a correctness bug. Right? If you have a data race, it is you'll get the wrong result. And the irritating thing is that you can run it on your 4-core machine and get the right result 1,000 or 1,000,000 times, and then somebody runs it on an 8-core machine and starts getting incorrect results every 10 times they run it, right? So you really want to run a tool that helps you detect data races. So here's one more, and perhaps in some ways my favorite, it's the most complicated way to solve a data race is to avoid having the data race in the first place. And we do this by doing a divide and conquer. We divide up our input set into things that are completely independent, compute them independently, and then combine them manually ourselves. So this is a recursive implementation instead of a loop. There's no loop in here. A recursive implementation of our parallel count. And again, it looks a lot like fib or the Q-sort that we saw before. Sorry, wrong button. So we divide our range into 2 ranges. We find the midpoint, and then we do a parallel count on the first part of the range and a parallel count on the second part of the range. And because they are disjoint ranges, they're completely independent. And we can do them simultaneously, and so we specify them as parallel. And again, because it's recursive, the amount of parallelism we get depends on how big our range is. So if our range is 10 elements, we're not going to get very much parallelism. That's okay. 10 elements doesn't take very long to compute. But if it's 1,000,000, we'll get a fair amount of parallelism. Now, it's worth pointing out, okay, and then here we combine the results at the end. There's no race. There's no single data location that is being written to for multiple parallel strands. Note that this whole function might be called, at the 20th level of recursion. So what's going on here is that this result is a local variable to this recursion. And so when we write to it, there's no race. But that doesn't mean that we have stopped running in parallel with all the other occurrences of this function. Okay, so it's important that this is compositional. You can look at one function and reason about the parallelism that's happening within that one function without having to worry too much about whether there's other parallelism going on in the caller to the function and so on. Okay, it's nicely modular that way. By the time we exit this function, anything that we've done in parallel is done. It's worth pointing out this little funny thing up here. If our range is less than 32, we revert to a serial program. Why did we do that? Well, I mentioned that spawning is a lot cheaper than creating a thread. And it's pretty cheap. You want to create spawns or TBB runs or whatever pretty liberally to really take advantage of whatever the core count happens to be. As you go to faster machines or with more cores, you want to get that speed. But they're not free. They're both recursion and spawning add some overhead to the program. And we want to minimize that overhead. When we get down to a really small number, it makes sense to just switch to serial, non-recursive serial implementation. It's called coarsening, and it's a way of improving performance. You do give up a little bit of parallelism, but the amount of parallelism you give up is small enough generally that you don't notice it. Okay. Question?
How does this interact with standard recursion optimization?
This isn't really tail recursive because of the sync.
Yeah.
I'm pretty sure the Silk Plus compiler will not be able to take advantage of tail recursion here. I haven't really thought that much about that, about whether there's a tail recursion optimization that could be done here. Actually, you can manually do a tail recursion thing that is beyond. You can talk to me later if you want to see how that's done. I have to think that through. Question?
Please use the microphones. We have 3 probably here.
Right. So I have been trying to repeat questions, but yes, if you can actually ask your questions at the microphones, that would be great. Especially if we have time at the end for question and answer. Okay, the next problem. This is my favorite because there's so much interesting stuff inside the CPU that's going on. Do you have a question or do you want to? Yeah.
I have a comment actually about data races. You mentioned that data race is a correctness problem. That's not actually true, because data race can not only lead to incorrect result, it can lead to undefined behavior. For example, it can launch nuclear missiles if your computer is attached to them.
Right. So launching a nuclear missile when you're not intending to, in my mind, is a correctness problem. That might be a value judgment on my part. But yes, a data race is undefined behavior. It doesn't just give you the wrong answer in that one memory location. It could actually corrupt the memory location so it has neither of 2 possible correct answers. And it can end up with very strange things, especially if there's a pointer involved. False sharing. False sharing, in order to understand false sharing, you have to understand a little bit about the architecture of a modern CPU. We have here 2 cores in a modern CPU. Each one of them has an L1 cache. I'll get to you in a minute. And the first core wants to read this location, this orange location, the one that's holding B. So when it reads it, it doesn't just read memory from that one location. It reads the entire cache line, which on an Intel processor is 64 bytes. It reads all that at once, and it puts that into its L1 cache. Now, L2 wants to write to the memory location D. Now notice there's 2 separate memory locations, D and B, 2 different memory locations. There's no race. But in order to do that, it has to invalidate, first, it has to invalidate core 1's copy of the entire cache line. It doesn't distinguish in anything smaller than the cache line for that purpose. Then it does a read, modify, write on D. But now core 1 wants to read B again. So it says, no, you took my cache line. I want it back. This is, we sometimes refer to this as cache ping pong. The cache line just going back and forth between different cores, L1 caches. It goes through the memory subsystem. Depending on whether the cores are on the same socket or not, if they're on separate sockets, it may actually go through main memory. Main memory is a lot slower than the CPU. It's a lot slower than L1 cache. So this kind of ping pong is a performance problem. It is not a correctness problem. Unless you miss a timing thing that has to happen, it's not a correctness problem. It gives you the right result, but it takes longer than it should. All right, question?
Yeah, I was going to ask, if we have a situation where all cores are fairly loaded, like we have a server with many tasks submitted, so it wouldn't make sense to try to spawn something if we cannot get a free core to execute it.
Okay, yeah, good question. So if the machine you're running on is loaded for some reason other than parallelism, like you're running, 100 copies of the same program, does it make sense to use parallelism? Probably not. Depends on your application. If the load is really constant and full, then no, you're not going to gain anything from going parallel. But if the load fluctuates a lot, go ahead, spawn some things, and if the load drops because one of those other programs finished and the CPU has become available, you can take advantage of the extra cycles that are available. So it really depends. All right, how do we fix false sharing? False sharing is about this misalignment of data. It's about having two things operating on the same cache line at once. And the example here is an M by 7 or a 10,000 by 7 array. 7 is a funny number in computer science. It doesn't quite fit. A single row of this array doesn't completely fill a cache line, but it almost fills the cache line. And then when we do a parallel operation here, the Silk 4, say the first iteration of the Silk 4 running in parallel with the second iteration will both access that row, this cache line here, that is the first row and the second row, because they overlap on the cache lines. That's our false sharing problem. We don't want those two things operating in parallel to share that cache line. So the way we fix it is two different solutions showing up here to get effectively the same result. One is instead of representing a row as a normal array, just simply a second dimension on the array, we encapsulate it in a struct, and we specifically align the elements in that struct using the C++11 align as directive, declaration. So this row will now always be aligned on a 64-byte boundary, and for the Intel processors, the 64-byte boundary is the same as a cache line. And then when we have an array of these rows, we end up with this kind of arrangement where each row is on its own cache line. So that's one way to do it. The other way is to just actually round up our size from 7 to 8 using this really straightforward calculation that says how to round something up to the next cache line. And then instead of making our 10,000 by 7 array, we have a 10,000 by 8 array, even though we're not using the 8th element of any row. Okay, it's unused. But that prevents the iterations of a Silk 4 from accessing the same cache line at the same time. Unfortunately, cache alignment stuff is really non-abstract. You have to understand a little bit about the specific machine you're compiling for. Just a few generalizations that help. It would be really nice if we had linguistic help for this kind of thing, but we haven't developed a really good model for that yet. All right? It's really a pragmatic problem rather than an abstract problem at current. We don't have an abstraction for it. There was a question, but did I answer your question?
Kind of. I was going to ask, is there a way to make that portable, or does it recompile that?
Right. The question is there a way of making it portable? And not really. You can use some generalities, use a big enough cache line thing, and you'll hit all of the current architectures and anticipated architectures. CPU vendors are very loath to change cache line size because there's a lot of assembly language that actually assumes cache line sizes. So, yeah. Okay. And the last thing I'm going to mention in the parallelism bug, because we're running out of time, is just not having enough parallelism. So there's actually a mathematical way of calculating parallelism. It is the total amount of work divided by the work of the longest path through the code, the longest serial path through the code, which is we call the span. Okay, the work over the span is the parallelism. And in our example here, where I've assigned weights to the various things, we have 4 things happening in parallel. Okay, our spawn, 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 and then the last thing is also in parallel with all the spawns. But one function is much longer than all the rest. That's shown in yellow. And if you calculate the actual cost based on these hypothetical weights, we see that the span is 23 and the work is only 39. So the parallelism is less than 2. Parallelism in less than 2 means that you can't even fully saturate a 2-core machine. So if you have 4 cores, you are not going to get 4x speedup. You will get less than 2x speedup with this problem. Okay? So it means something's wrong here. You either cannot find enough parallelism in your program, or you need to really look at this long function and see if it can be subdivided into parallel tasks, something like that. And really, it's going to depend on your program. The last thing I'm going to mention are the serial challenges. Well, parallel programs have a subset of them that is serial, and they have all the challenges of serial programs, but sometimes they're magnified. So the CPU is much faster than the memory. 2 CPUs are that much more faster than the memory. So you have this little straw connecting the CPU to the memory. If you don't have good cache locality and so in your program, it'll be even worse when you go parallel. Debugging, if it's hard enough to do debugging in the serial program, parallel program is even harder because there's things happening at the same time. Concurrent programming is also harder to debug. Nice thing about parallel program is you can usually run it with one thread until you've gotten all the serial bugs out of it, but then you have to, if there's race conditions or things like that, you're going to at some point have to debug it multi-threaded, and we're still working on better and better ways to debug that. Okay, so I hope I've shown that this is real, that there's a bunch of different programming models out there from Silk to OpenMP and TBB and so on to do parallel programming, and that you need to know how to do it. So there are more sessions. This is like the kickoff session of the entire track of parallel programming sessions in CppCon. So I encourage you to go to others. I have a talk tomorrow about how to decompose a problem so that you can execute it in parallel. And get the tools to do it, and get some tools to help you debug it. Things like performance analyzers and race detectors shown here. There's a resources page here. At some point, somehow, through the CppCon website, I will find a way to get these slides to you. So look for them, but that has not been determined. OK, so that's it for my time. I think we have like 15 minutes before the next session. Is that right? So I'm happy to stay around for a little bit of while and answer questions either with the microphones or without. But thank you very much for coming.